Okay, we will do the fifth question of assignment 3. Okay, so we have to state the FM signal with the Bessel function. Okay, and we have to draw the power spectrum for different value modulation in the value of modulation index, actually for 2 values. Okay, so I hope this is not much difficult question, because in our reference book this compact form is already given. Okay, so this is another representation for FM modulated signal. Okay, frequency modulated signal. So you can see here, instead of a function original FM signal, we have a function of a function. No? So here we have collection of sinusoidal signals. So these are sinusoidal signals. So we can say this is a collection of harmonics. Okay, so this frequency modulated signal representation, we can represent our modulated signal, frequency modulated signal, as a collection of harmonic using Bessel function. Okay, so this Bessel function is used to find the coefficients, these coefficients. Okay, so we can simply use Bessel function table to find the coefficients. Okay, for different n and different beta. Okay, beta is modulation index. Okay, so you can see that. Okay, we will start. Okay, so we have our modulated signal. FM modulated signal, XFNT AC cos omega CT plus integrator KF. Okay, so here we have our modulated signal XFMT. Okay, AC cos omega CT plus KF integrating of message signal with respect to T within time. So T is the time of the signal, message signal. Okay, so this is carrier signal, carrier amplitude. This is carrier frequency. This is frequency sensitivity. Okay, so we know that KF into VM, maximum amplitude of the signal, is equal to frequency deviation. Okay, and if we divide frequency deviation from modulating frequency, we have modulation index. Okay, here it is beta. Okay, so and also we know that this frequency deviation refer how much our modulated signal is shifted from carrier signal. Okay, so so maximum frequency. Okay, for maximum frequency for modulated signal, FM modulated signal, we have FC plus F delta. Okay, and minimum modulated frequency, we have FC minus F delta. Okay, so these are the relationship between frequency sensitivity, frequency deviation, and modulation index. So you have to remember this thing. Okay, and you already know that this is MT is our message signal. So normally message signal is practically it is an audio signal. It may be audio signal, video signal, or image signal, anything. Okay, so this is the MT, our message signal, baseband signal. So normally for analytical purpose, we are selecting this MT, our message signal, as a sinusoidal signal. Okay, AM cos omega MT. So this is a sinusoidal signal, and one sinusoidal signal is there. So we called it single tone. Okay, because the sinusoidal wave will generate one tone. Okay, so we call this single tone message signal. Okay, message signal. So if we select our message signal as a single tone, it will called single tone modulation. Okay, it is said that single tone modulation, signal tone frequency modulation. Okay, so for single tone modulation, you have, if you want to write the waveform for single tone frequency modulated signal, okay, you have to send this message signal through an integrator. Okay, through an integrator, and you will have integrated signal. Okay, so physical implementation of this integrator is somewhat difficult. Okay, somewhat complex. Okay, but these are used in many communication system in receiver side and also in transmitter side. Okay, so if we send our signal MT through this integrator, we have AM cos omega MT omega M. Okay, so so integration is AM sine omega MT. So here it is not AM. Okay, AM cos omega MT. Okay, so if we integrate it, we have AM sine omega M by omega M. Okay, so this is our integrate output. Okay, so if we write down modulated signal, okay, if we write down modulated signal, okay, we have X FMT as AC cos omega CT plus AF, this output, integrate output, AM by omega M sine omega MT. We have this signal. Okay, so you can see that this is modulation index, that is beta. So if we write our modulated signal, we will have XFMT AC cos omega CT plus beta sine omega MT. So you can see that this is a function of a function. Okay, so frequency domain analysis is somewhat hard. Okay, but we can write this signal in the form of as a collection of harmonic using a Bessel function method. Okay, so we have this signal XFM signal also in this form as a collection of harmonics. Okay, so here we have AC. Okay, Jn beta, okay, cos omega C plus n omega MT in this form. Okay, so you can see that if you want to find the Fourier transform, you can directly find it, okay, without a problem. But here we can't do that thing directly, that Fourier transformation. Okay, we have to, one way is that we can assume this as a narrowband signal, and we can then we can approximately estimate the frequency domain signal. Okay, but with this format we can easily do this. Okay, so this is better, this format is better for frequency domain analysis. Okay, frequency domain analysis, this method is better. Okay, so in our assignment, we have to only state this. Okay, no need to derive this. Okay, we have to state this and convert this to frequency domain signal, frequency domain representation. Okay, but for the completeness of our session, we will try to derive this. Okay, so before going for derivation, I like to tell two or three things, few things. Okay, one thing is that any transmitter and receiver, okay, generate and receive only real signal. Okay, real signal, because normally in transmitter, the signals are generated using oscillators or some device like microphone, camera, so on. Okay, so anyway, these are real signal, not complex signal. Okay, but for the analytical purpose, we sometimes represent this real signal, this transmitting and receiving real signal, TX and RX real signal, okay, real signal as a part of complex signal. Okay, complex signal. This is for analytical purpose. Okay, so you know that if we have EJ theta, okay, let's say omega naught t, this complex exponential signal, okay, we can represent this using Euler formula. We can write this like this, J sine omega naught t, like this. Okay, so you can see that this is real signal, real part, and this is the imaginary part. Okay, so imaginary part. Okay, so you can see that we can say, okay, we can represent this real part as a real of this real part of this complex exponential signal. Okay, so likewise we can represent some real signal using as a part of complex signal. Okay, so this model is called complex uh, equivalent equivalent transmit or receive signal model. Okay, signal model. So you can find more details in there, in many books, in many wireless and digital communication books. This model is stated, this model is described. Okay, so in Andrea Goldsmith wireless communication book also you can find this complex signal models. Okay, so here also it is mentioned that oscillators normally generate sinusoidal real signal. Okay, but for the analytical purpose, okay, analytical purpose, okay, we represent this signal, okay, we see as a part of complex signal. Okay, for analytical purpose. Okay, so this is our signal model for transmitted signal, transmitting signal. Okay, so we can write, so this is a transmitted signal, sometimes we called it as passband signal. Okay, so we can write our transmitted signal or passband signal as real of ut e j omega ct. Okay, so this is carrier component, and this is baseband component. We call this complex baseband signal, baseband signal. Okay, so here we sometimes use this model to represent our signal, our FM modulated signal. Okay, okay, so this is the transmitting signal, or we can say it is a modulated signal, passband signal, and this is our baseband information signal, and it is in complex form. Okay, so this UT is a complex signal. Okay, so this UT is a complex signal. Okay, so you can find more details for this model in this book. Okay, but we are not much going to discuss about that. Okay, the other thing is the Bessel function. Okay, other thing is Bessel function. Okay, Bessel function, and I also don't have a full understanding about this Bessel function. Okay, so anyway, you can find some information in Wikipedia. Okay, so it is said that a Bessel function is a Bessel function is the solutions for this differential equation. Okay, and this Bessel function, there are many type of Bessel function. Okay, this is original Bessel function. Okay, first kind, second kind, likewise. Okay, modified Bessel function, Henkel function. We have several type. Okay, so here we are in our example. We can use this Bessel function with the first kind Bessel function. Okay, first kind Bessel function. Okay, and this one is somewhat another definition, but it is important one. Okay, actually we are using this definition. Okay, for our derivation. Okay, we are using this definition. Okay, so you can see that this is the Bessel function n and x. So two variables are there, n and x. Okay, so you can see that we can evaluate this. So you can see that here it is a function of a function, no? And this one also function of a function. Okay, so we can evaluate function of a function directly using this Bessel table. So table is formed to evaluate this integration. Okay, for example, if n is equal to 2 and if say x is equal to 5, okay, so it is cos 2 tau minus 5 sine tau d tau 0 to 5. Okay, so if we integrated this, okay, we can see the Bessel function. Okay, what is the corresponding value for n and x? Okay, so here we have a Bessel table. Okay, so we have n is 2. Okay, and we select x is 5. So this value will get as the answer. Okay, 0.007. Okay, so likewise we can use Bessel table, this Bessel function table. This is a first kind Bessel function of first kind. So this table to evaluate that integration or to find that integration value. Okay, so we are using that one in our derivation. Okay, and also you can notice that for Bessel function, there is a property. Okay, so you have to use this property also. So here it is said that if you have minus value, minus n value, say -1. Okay, so Bessel function is -1 is equal to -1 to the power of 1. Okay, and that value. Okay, so we will use this property also in our derivation. So we will see how we can use it. Okay, so let's start our derivation. Okay, so you can skip this derivation if you are not interested, because this is not compulsory. Okay, so we will try to do the proof. Okay, okay, so I will here again write our modulated signal. Okay, I will write my modulated signal, our modulated signal. FMT is equal to AC cos omega omega CT plus beta sine omega MT. So this is our modulated signal, no? This is a modulated signal. Okay. So now I am going to represent this signal in complex form. Okay. Complex transmitted signal model. Okay. So I can denote this signal. Okay. I can denote this signal as the real part of. Okay. So this is my pass band signal. Okay. This is my pass band signal. Okay. As real part of, okay, e to the power minus j cos omega ct plus beta sine omega mt. Correct? Okay. So we can write this because this is a cos value. Okay. This is a cos value and this is cos theta. Okay. So if we consider this as theta or omega naught t, okay, so we can write this. Okay. Yeah, using the Euler formula like this. Okay. Okay. And at that time our modulated signal, okay, our modulated signal is this, the passband signal, our modulated signal. So this is FMT, modulated signal, passband signal, and we write it as a complex waveform. Okay, complex waveform, real part of complex waveform using the Euler formula. Okay, so I hope it is clear. Okay, so now I can separate. Okay, so you can see that here we have the baseband signal and also the carrier component. So I will try to separate this baseband signal and carrier signal here. Okay, carrier signal here. Okay, so I can do this real. Okay, so you know that we can write this simply as e to the power minus j. Sorry, I'm sorry, the cos is not here, no? Sorry, I done a mistake. Okay, so here you can see that if we consider this as theta, okay, consider this as theta, okay, ej theta is real part of ej theta is equal to cos theta, no? Cos theta. So I have to use this theta only. That means this theta, not cos. Okay. So here we have j, okay, j omega ct plus beta sine omega mt, because this is the t, no? This is theta. Okay, this is theta. Okay, so cos value is not here. Okay, so I can write this as cos minus j beta sine omega mt e to the power minus j omega ct, like this. Sorry, this is not minus, this is plus. Okay, this is plus. Okay, so I can write this like this. Okay, so here this is cos omega ct plus beta sine omega mt. This is theta. We can consider this as theta. Then I can write this as a real part of e to the power this theta, this section from here to here. Okay, so only omega ct plus beta sine omega mt is there. Okay, so I have divided it to two parts. So I can write this e to the power j beta sine omega mt e to the power j omega ct. Okay, so you can see that this is equal to ut. Okay, this is equal to ut, and this is the carrier part. Okay, carrier part. Okay, so this is our baseband signal, and this is carrier signal. Okay, and this is the modulated signal. Okay, so I can write this as, okay, so this ut is complex baseband signal. This ut is complex baseband signal. Okay, so now I am getting this baseband signal, complex baseband signal. Okay, So I am getting the complex baseband signal. Okay. So I denote it as SBT. This is our complex baseband signal, complex information signal. Okay. Complex information signal. Information signal. Okay. So it is equal to e to the power j beta sine omega mt. Correct. So this is our complex signal, complex baseband signal. Okay. Okay. So now I am going to so what you can see here. Okay. So if I ask you a question, okay, so you can answer that one. This signal, this signal, our complex baseband signal, SBT, is this periodic or not? Okay, and if periodic, what is the period? So can you find this? Okay, can you find this? Okay, so before going further, stop here and try to verify this is a periodic signal or not. Okay. So anyway, we will do this. Okay. So you can see that this is sine omega mt. Okay. So here we have sine omega mt. And you know that every sinusoidal signals are periodic. Okay. So sine omega mt is a periodic signal. So this is a periodic signal. Okay. So period is, okay. Here the period is, let's say it is T naught. Fundamental period is 2π by omega m. Okay, so every sinusoidal signals are period. Okay, and another point you have, I think already you can remember these things you have learned in your signal and system subject. Okay, so any exponential signal like omega t, omega naught t. Okay, so this also periodic signal. Okay, and the period is here also 2π by omega naught. Okay, so this one and this one are periodic signal. So you can see that it is a function of a function. Okay, and this sine omega mt is periodic signal, and the period is 2π by omega, and this e, the complex signal, also period, and the period is same, this 2π by omega. Okay, you can prove it. Okay, so try to prove it. The condition is for the periodic is that x t plus fundamental period is equal to xt. So using this condition, I hope you can prove this and find the t value. Okay, find the t value. Okay, if you interest, you can try it as a homework. Okay, so you can use this periodic condition xt plus capital T naught equal xt. So using this, you can prove this periodic or not. Okay, and also you can find this T naught using this identity. Okay, you can try it in as a homework. Okay, but here I'm not going to do this. Okay, so what is the final answer you get here? Okay, so final answer is this is period, this is periodic signal, this is periodic signal, and period is T naught is equal to 2π by omega m. Okay, so that is the condition you have to take. Okay, so this is a periodic signal, and you know that. Okay, and also you have learned in your signal and system any periodic signal, actually not any periodic signal. Okay, but we can set most of signal. Okay, most of normally we said that any periodic signal. Okay, any periodic signal. So if any periodic signal xt, okay, with the period of t naught, okay, can be represented as a collection of sinusoidal. Also in sinusoidal, you can represent as a collection of complex exponential terms. Okay, like this: minus infinity plus infinity Cn e to the power Jn omega naught t. Okay, so here the period is 2 pi by omega naught. Okay, so can you remember this? Okay, what is this? This is actually Fourier series representation of periodic signal, no? Periodic signal. Okay, so you can express, we can say any. Okay, we can say any. Okay, but actually not any. Yeah? Actually not any. Okay, any signal, any periodic signal as a collection of complex exponential harmonics or complex exponential terms. Okay, using the Fourier series representation. Okay, and I think you can remember, you can find these coefficients. Okay, you can find these coefficients. You have to do an integration. Okay, it is 1 by t naught integrate within t naught. Okay, integrate within t naught xt e to the power minus j n omega naught t dt. Okay, so using this integration you can find the Cn value. Okay, so I think you can remember that this is Fourier series representation of a periodic signal. Okay, so our baseband complex signal, this signal is also periodic signal. So I am going to represent this signal as a collection of harmonics. Okay, because we can see that in that format, the XFM modulated signal is represented as a collection of harmonics. So I'm going to do that one here. Okay, so I'm going to represent my passband signal SBT as a collection of harmonics, complex exponential harmonics. So I can write it. Okay, I can write it like this: SBT, my complex baseband signal, is equal to minus n is equal to minus infinity plus infinity Cn e to the power Jn omega naught. Here is B, the fundamental frequency of SB is n omega m. Okay, omega m. So I use that instead of omega t, omega naught. Okay, so here omega m, Jn omega m t. Okay, and I can evaluate this coefficients using 1 by t integrate within period, within one period. So here the period is t naught is 2 by omega. Okay, so I use this period as minus 5 by omega m. Here this is omega m. Okay, and plus 5 by omega m. Okay, it is correct, no? And this also we have 2 5 by omega m. Okay, so I select my limit as minus 5 by omega m plus 5 by omega m, so that I'm going to integrate it within one period. Okay, within one period, within one fundamental period. So my SBT is, okay, so here xt is equal to SBT, and SBT is e to the power j beta sine omega mt. Okay, so I have e to the power j beta sine omega mt. Okay, and we have e to the power minus, okay, e to the power minus j omega m, sorry, n is there, no? E to the power minus j n omega mt dt. Okay, so I have this coefficients. Okay, now, okay, now I'm going to write it again. So 1 by t, here it is t naught. Okay, t naught is equal to 2 pi by omega m, and we have omega m by 2 pi. Okay, I'm sorry, AC is also there. Okay, because you can see that because this AC should be included here. Okay, AC should be included here, and AC also here. Okay, so my complex my complex baseband signal is AC e to the power j beta sin omega t. So here AC is there. Okay, and here also AC should be here. Okay, here AC, so here AC should be here. Okay, so I have AC also here. Okay, AC omega m AC to 5. Okay, minus 5 omega m plus 5 omega m. Okay, and I get e to the power j j yeah j t. Okay, I also can get, no, I can't get the t. Okay, so I get t j here. So I have beta sine omega mt plus omega mt dt. Okay, so if I go to that Bessel function again, okay, so look at this one. Okay, so jnx is equal to 1 by 2 5 minus 5 to plus 5 e to the power j x sine tau n tau d tau. Okay, so you can see that it is somewhat similar to my expression, no, to our expression, this expression e to the power j beta, okay, beta sine omega mt plus plus wmt. Okay, sorry, here n is also there, so n is there. Okay, n omega mt. Okay, beta sine omega mt plus n omega mt, this n is there. Okay, I put that 10. Okay, so you can see it is somewhat identical to our Bessel function definition, the second definition. Okay, so here you can see it is tau. Okay, and here it is t. Okay, so tau, here it is one, only variable is that tau. Okay, so I'm going to form my expression. Okay, so you can see that we can calculate this coefficients using a Bessel function using a Bessel function value, using Bessel function table. If I can adopt this to that Bessel function definition. Okay, so you can see the basic structure is there. So within some modification, I can do this. Okay, so we have a hope, no, we can do this. Okay, so you can see that Cn, sorry, so you can see that. Okay, here we have tau, no, here we have tau instead of omega naught t, we have tau. Okay, and here also we have tau. So I will substitute this omega mt as tau. Okay, and you can see that it is in dt, but in Bessel function it is in d tau. So I am going to convert this to d tau. So d tau by dt is simply omega m. Okay, dt. So dt is equal to d tau by omega m. Okay, and if you consider the limit, you can see that also we have to change the limit. No, now we are going to change the variable of this integration. Okay, so we have to change the limit also. Okay, let's see what happened to the limits. Okay, so you can see that tau is equal to omega mt. Okay, so here t is limit into -5 omega m, the lower bound, lower limits of t. Okay, lower limits of t. Okay, so t is limit into -5 by omega. So then what happened to tau? Tau is equal to omega m by t, no? Omega m by t, t is -5 by omega m. So you can see omega m cancel. So tau is limiting to -5. Okay. In same manner, when t is limiting to, okay, if t is the upper bound, upper limit, okay, t is limiting to +5 by omega n, +5 by omega n. What happened to tau? Tau is equal to omega m +5 by omega n. Then omega m cancel out. Then t is limiting to +5. Okay. So I think most of others are directly related with the Bessel function. Okay, so if I write this Cn, okay, this Cn as, okay, so you can see that if I apply d instead of dt, I have to apply d tau by omega m. So I have to here apply d substitute d tau by omega m. This omega m and omega m will be cancelled. So I have AC by 2/5 integrate. Okay, here the upper limit, lower limit is changed to -5. Upper limit is changed to +5. No, now tau is -5 and tau is +5. The upper limit is changed to +5. Okay, and here we have e to the power j beta sine tau plus omega mt means tau, so we have n tau. Okay, dt. Okay. So what happened if you check this part? This part, it is directly related with the Bessel function. No? It is directly related with Bessel function. So you can see that 1 by 2/5 minus 5 to +5 e to the power I x sine tau. Here we have beta, okay, sine tau minus sine tau d tau. Okay, so we can say that it is ij, that is okay, e to the power j x. Instead of x, we have beta. Okay, and we have n also, so it is jn beta. Okay, in our case we can write it as jn beta. No, so this part we can write as jn beta simply. Okay, so cn is equal to ac jn beta. Okay, so if I substitute this and write my baseband signal, this one, okay, so I can write my baseband signal. Okay, I can write my baseband signal SPT as n is equal to -infinity to +infinity. So here Cn is equal to AC Jn beta e to the power Jn omega mt, correct? So I can write my complex baseband signal as this. Okay, so I'm going to substitute it to my total signal. Okay, total signal. Okay, that means to this signal. Okay, so I will write it again here. Okay, so I have my total signal. Okay, complex equivalent signal as real part of, okay, real part of this SBT e to the power j omega ct. Okay, like this. Okay, so we have get this xfn. This is our total modulated signal. Okay, this one. Okay, this one. Okay, so this AC e to the power j beta sine omega t is simply SBT, no? Our baseband modulate baseband complex signal SBT. Okay. Okay. So if I substitute it, okay, so I substitute it here, you can see that. Okay. Okay, so my total modulated signal will become, this is my total modulated signal, will become real part of, okay, real part of, so collection. Now we have a collection, okay, collection of x equal to minus infinity to plus infinity. Okay, AC Jn e to the power Jn omega mt, and we have e to the power j omega ct. Okay, so I can write this by further simplification. By further doing simplification, I can write this as minus infinity to plus infinity. AC is there, Jn beta. Okay, so here Jn beta, and Jn beta is there. Okay, e to the power. Now I can get Jt, okay, and omega c plus n omega m is there, no? Like this. Okay, so you can see that this is simply, we can say omega naught or something, and j omega naught is, we can write as theta. Okay, so you can see that it is a real part of e to the power j theta. So what is the real part of a to the power e j theta? That is cos theta, no? So I can write my modulated signal using the Euler formula. Okay, you know that real part of e to the power j theta is equal to cos theta. Okay, we have seen this. Okay, so I can write this. So using same concept, same identity, I can write my modulated signal. Okay, my modulated signal xfmt as collection of minus infinity to plus infinity. Okay, so AC is there, Jn beta is there, and e to the power j omega naught t. Okay, so we have cos omega naught t, no? That is this part, omega c plus n omega m t. Okay, so this is our modulated signal, and we write it as a collection of harmonics with Bessel function coefficients. Okay, so we can get it, no? We have derived. Okay, so let's see it. Okay, here we have AC in minus infinity plus infinity Jn beta cos omega c plus n omega mt. Okay, correct. So we have same one, no? AC Jn beta cos omega c plus n omega mt. Okay, so our derivation is okay. Okay, now we will move to the question. Okay, so you can actually skip this derivation if you need. Okay, but I am doing this for the completeness of the session. Okay, so we will move to our question quickly. Okay, so we have now we have a state. Okay, so in our first part we are asked to state xfm t is equal to ac n is minus infinity to plus infinity jn beta cos omega c plus n omega m t. Okay, so this is the answer for our first question. Then we have to find the power spectrum. No? Then we have to find the power spectrum. We have to draw the power spectrum for these two modulation index. Okay, so we will see it generally. Okay, so anyway, it is a spectrum. No? Okay, so normally actually up to here we didn't do any power spectrum. No, we have drawn only frequency spectrum. Okay, so if I tell you something about that. Okay, if I tell you something about that. Okay, so we know that we have found many frequency spectrum. No, frequency spectrum. So here what you have found actually, you can here you plot. Okay, frequency spectrum, you found some frequency component. Okay, frequency component and its relative amplitude. Okay, so these are normally voltage signals. So in modulation normally we are using voltage. Okay, so this our uh, information signal, that is a voltage signal. The voltage is varying with time. Okay, and oscillators also, that means for our carrier signal also we are considering voltage signal. That means voltage is changing with time. Okay, so these are voltage signal. So amplitude is normally a voltage value. So here in frequency spectrum normally we plot voltage. Okay, voltage, or we can say amplitude versus frequency. Okay, so this is the frequency spectrum. So sometimes this is called amplitude spectrum. Okay, so sometimes these are called amplitude spectrum. Okay, so we are plotting, or we are finding the amplitude with respect to frequency. Okay, but what is power spectrum? In power spectrum we have to normally, so you can the name or name itself imply that we have to plot power. Okay, power of different frequency component with frequency. This frequency can be f omega. Okay, so we have to put the power here. Okay, so so if I consider cos signal, okay, so if I consider cos omega naught t, this signal, okay, so you know that let's say this is a, okay, a cos omega naught t, okay, so you know that Fourier transform we will have AC, not AC actually, A5 delta omega minus omega naught plus delta omega plus omega naught. Okay, and if you write it with respect to phi, sorry, with respect to normal frequency, here we find with respect to angular frequency, it is 2 f naught t. Okay, so here we have a by 2 delta f minus f naught plus delta f plus del f naught, like this. Okay, so I will plot the frequency spectrum of here. Okay, so if I plot the frequency spectrum, okay, if I plot the frequency spectrum, okay, I have two components. One is plus f naught, okay, another is minus f naught. Okay, and amplitude is a by 2 and a by 2. Okay, so you know that power of this total signal is, okay, we have found this already. So power of this total signal is a square by 2. This is the power of this sinusoidal signal. Okay, so if I plot the power spectrum with respect to here, okay, what we have to get, if I get the square of these two components, if square of this amplitude, I have a by 2 square and a by 2 square for these two components. Okay, so find the total power. We have to add these two power, no? To find the total power of the signal, we have to add this power. So we will get a to the power a square by 2, no? A square by 4, a square by 4. Then we have a square by 2. And you can see that it is equal to this, no? So it is correct. Okay. Correct. So simply, if you want to draw the power spectrum, draw it with respect to f. First thing is draw it with respect to f. And what you have to do is you have to simply get the scale of amplitude and plot it. Okay. So you can keep this in your mind. Okay. And you can use this. So normally we have to, in many cases, we have to find the power spectrum for sinusoidal and maybe sometime complex exponential terms. So you can, if you have idea, you can directly apply it. Okay, but this method we can't apply it for all signal. Okay, sinusoidal and some signal we can apply this. Okay. So that is how to draw the power spectrum. Okay. So first of all, to draw the power spectrum. So anyway, we will see the frequency spectrum. Okay, frequency spectrum of this signal. Okay, so I think you can simplify it. Okay, so here you have to find the frequency spectrum of here cos signal. Okay, cos omega c and omega mt. Okay, so you can consider this as omega naught. Okay, then you can simplify in the frequency spectrum. Okay. So anyway, I will write it again here. Okay. So we have xfm t, the waveform time domain signal as n minus infinity to plus infinity. Okay. AC jn beta cos omega c plus n omega m t. Okay. So you can consider this as omega naught. Omega naught. Okay. Then you will have the what is called the frequency spectrum as I will draw with respect to f. Okay, not with respect to omega. Okay, because when we are drawing the power spectrum, it is somewhat easy. Okay, so we can say that it is half delta f minus f naught plus delta f plus f naught, like this. Okay, so this omega ct is simply we can write as to 5fct, and we can write this as to 5fmt to 5fm fm. Okay, so I can write this. Okay, so if I write this, okay, so the frequency transformation, okay, so Fourier transform of this xt, okay, Fourier transform of this xt, normally we denote it as capital F x. So here it is f. We can write it as n minus infinity to plus infinity. AC is there, Jn is there, AC, Jn, beta is there. And we have, this is half, okay. And delta f minus f naught, okay. So f naught is simply, you can say that this is 25 fc. Here it is not plus, okay, so this is plus, okay, 25 fc, 25 fm, okay. So you can write this as 25, okay, 25 fc plus nfm t, okay, 25 plus fc plus nf, 2 fc plus nft, okay. So this is simply f naught, no, this is simply f naught, 25 f naught t, okay. So this is the f naught, okay. So I can write f minus f naught, that means fc plus nfm, okay. This is one term, and plus delta f plus f plus f, oh, sorry, yes, f plus f naught. F naught is simply fc plus nfm, okay. This one, okay. So we have this one as a frequency spectrum, okay. So if I draw the frequency spectrum for general case, okay, for general case, if I draw the frequency spectrum, okay, we have this is 0, okay. So we have fc minus fc in fm, okay, fc minus fc in fm, okay, and plus fc minus nfm, okay. So so first take this n as 0, okay. So we have different harmonics, no, so you can see that we have different, this n is the variation, varying, we have different component like this, okay. So we will see how it happens, okay. So I first thing, this is with respect to f, this is 0 point, okay. So let's take n as 0, okay. So then n is 0, this is delta f minus fc, okay. So one part is here, this is for n is equal to 0, okay. So we have fc, and here also we have minus fc, okay. So this is for n is equal to 0, okay. Then n is equal to 1, it is fc plus fm, okay. So we have here fc plus fm, and here also we have minus fc plus fm, okay. And if fc is, the n is equal to 2, this is n is equal to 1, n is equal to 2, we have, okay, we have fc plus 2 fm, okay. And here also we have fc plus 2 fm total minus, likewise. So this will go to infinity, no, this will go to infinity, and here also this will go to infinity. So you can see that we have infinite number of harmonics, okay, frequency component. Okay. Uh, so what is the value here? Okay, so I get 0. Okay, so this is J0 beta, or beta value, some beta value, and this is J0, J1 beta, and this is J2 beta, and this is J3 beta, like this. And here also we have J1 beta, J2 beta, J3 beta, likewise. Okay, so so this n can also have minus value. So if I get one minus value, minus 1, we have Fc minus NFM. So here we have one component like this. So this is Fc minus Fm, that is n is equal to minus 1. Okay. Okay. So n is equal to minus 1. So you know that we have one property. Okay. Minus is that property with the Bessel function, this one, j minus nx minus n jnx. Okay. Okay, we have a special property, j minus n x, we have minus 1 to the power n j nx. Okay, so if n is equal to minus 1, okay, we have minus 1 to the power 1. Okay, minus 1 to the power 1. So this n is plus. Okay, that means minus 1 jn. Okay, jn 1. Okay, so that point we have minus value, no? So here we have minus value. Okay, here we have minus value this way. Fc minus Fm is this way, and it is also equal to J1 beta. Okay, and J2 beta is here. If you write minus 2 also, Fc minus 2 Fm. Okay, so you have minus 2 here, so minus 1 to the power 2, that means plus 1, no? So here you have plus value like this. Here it is J2 beta. Okay, so likewise you can write the component for minus infinity to plus infinity, so that you will get infinite number of frequency component. Okay, so likewise you can write the frequency spectrum. Okay, frequency spectrum, and this value you can find with the Bessel function. Okay, Bessel table. Okay, so for so you can see that this is for signal, sinusoidal signal. So if you want to find the power spectrum, okay, so you can simply get this value squared. Okay, so you have J2 beta squared, J1 beta squared, and also AC also there. Okay, AC by 2 is also there. Sorry, I forgot that. AC by 2 is also there. Okay, like this, and you have to square it. Okay, AC by 2, AC by 2 square. Then you can plot the power spectrum. Okay, so we will do this for one case. Okay, let's take as beta is equal to 1. Okay, let's take as beta is equal to 1. Okay, so we have, I will write my frequency spectrum again. Okay, frequency spectrum again, capital FM is equal to AC by 2, correct? Yeah, AC by 2. N is equal to minus infinity plus infinity. Okay. Jn beta cos, sorry, Jn beta Kn beta delta f minus fc plus nfm, okay, plus delta f plus fc plus nfm, okay, nfm, okay, like this, okay. So this is my frequency domain signal, okay. So I can draw, so I select that beta is 1, okay, beta is as 1, okay. So if I draw my frequency spectrum, let's draw it for few values, for few n values, okay. So we have 0 here. So if n is equal to 0, we have here fc, okay, and here also we have minus fc, okay, and we have 1. So this is equal to AC by 2 J 1 1. Okay, so J 0 1, because I select beta as 1. So this one also have J by 2 J 0 1. Okay, so if I select plus 1, so here we have FC plus FM, and here we have AC by 2 J1 1, okay, and here also you have AC by 2 J1 1. This is for FC plus FM but minus, okay. And if you find for minus plus 2, okay, it is FM, okay, and here it is also AC by 2 J1 2, okay, and here also you will get same value, AC by 2 J1 1 J1 2, okay. So here it is FC plus 2 FM, okay. So how to find this value? Okay, so you can simply find a Bessel function. So here this plus value is 0 1, okay, n is 0, beta is 1, okay. So you can go to the Bessel function table, okay. So you can have n value here and beta value here. So what is beta? Beta 1, beta is 1, this one, and plus 1 is n is 0. So it is 0.76, okay, 0.76. So this value is 0.76, okay. And what is this value? J11. J11 is 1, 1, 0.44, and J12 is 0.11. So here we have 0.44, 0.11, okay. So this one is 0.44, and this J12 is 0.11. And here we have the same value, no? This one is 0.76676, and J11 is 0.044, and J2 is 0.11, like this, okay. And if you find FC minus 1, okay, FC minus 1, can you remember that we have minus value, no? Because J minus 1 is equal to minus 1 1 J11, okay, according to that property, okay. So minus 1 1 is equal to minus 1, so you have minus 1 1, okay. So here this is 1 1, 0.44, and minus 1 1, that means you have minus value, minus 44, okay. So this is FC minus Fn, okay, okay, and AC by 2 is also there, okay. And if you want to find the value for minus 2, So this is 2 minus 2, and here it is 2, no, minus 1 is square, minus 1 plus is square, that means plus 1. Okay, so you have plus j11 again. Okay, so for fc minus fm you have plus value, and it is equal to this one, no, 1 2, sorry, here it is 2, no. Okay, so 2 1 2 1, so here it is 2 1. Okay, here it is 2 1, 0.1. So likewise you can find the frequency spectrum, and to plot the power spectrum, what you have to do, you can simply square this value and plot it. Okay, so this is amplitude spectrum, this is amplitude spectrum. Okay, so to power spectrum, because we have a sinusoidal signal, so you can simply square this value. Okay, so here you can square this value. Okay, fc plus 2 fm. Here also you can square fc plus fm. This value you can square. Okay, and for fc you can square this value. Okay, and for fc minus f1 you can square, and then square. When you do the square, then that one will go to the this side, no, so this will come to this side, plus side. Okay, so when we square it, we have this value. This value is square. Okay, so likewise you can have a power spectrum. Okay, power spectrum. Okay. So I hope you can do that question without a problem. Okay, so the next one you have to go it for 2 also. Then it is the beta is for 2. Okay, beta is for 2. Then you have to find the coefficients j12, j22, j23, j minus 12, j minus 22, like so on. Okay, so you can find it using the Bessel table. So here n is equal to beta is equal to 2. That means this row you have to go through this row. Okay, this row. Okay, then you can find j02, j12, j22, j32, so on. Okay, so you can find. So I hope this is enough. Okay, so here what we have done is that we have proved that Bessel function representation or harmonic representation of FM, the frequency modulated signal, and we have answered our 5th question. Okay, so we will stop.